And that's one of the issues with this lab. Which is why this was the lab that I had to edit out the most profanity from. All right, since this is off, and we're gonna predict how much tension we need, or therefore, and consequently how much mass we need, what we're gonna do is figure out what the linear density of the string is. So I need to know the length of the string. And my meter stick on the floor, of course. It is going to be tight, so I'm going to tighten it. All right. It is 177.1 centimeters.
Centimeter.
We need to know the mass of it, and fortunately we have a triple D balance here. Now, because the mass is going to be so incredibly small, we need to be careful about it. We need to either have it offset or have it zeroed. And that is off. And having seen students do this in the past, before I actually had to find the offset or zero it, that was the biggest source of problems. Almost. Down there. All right, it is 1.76 grams. Or 0.00176 kilograms. So the question is, what is the linear density? How do you find linear density again?
That's 5 minutes.
So 0.00176 kilograms divided by 1.771 meters, and we end up with 0.0009 something.
We got a scientific. I got a scientific.
Okay. What'd you get?
9.94 times 10 to the power of -4.
Okay. Units?
Kilograms by meters.
Kilograms per meter. All right. So we have the linear density. We need to call back that formula that if I have something, a wave traveling along a linear medium, the speed I know is frequency times the wavelength, but it's also going to be the tension divided by the linear density. For the first harmonic, well, I have this distance here, which is going to be from here to there. Is going to be the vibrating length. So the only time we're using the entire length is for when we find the linear density. Uh, 113.2. So my vibrating length. What did I just say?
113.2.
My simplest harmonic is going to be that. How many waves?
Half.
So L, that L there, is equal to a half of a wave, and so the wavelength is going to be 2 times that. Frequency, 60 hertz. That's the frequency of the electricity coming out of our outlets. Coming out and going in. So I have 60 hertz times a length of 2 times that, which is 2.264 meters, is equal to the square root of the tension divided by my linear density, which is 0.0009. So what is the tension?
The weight of the mass.
What'd you
Is
say?
it the weight of the mass? If we're saying that.
Yeah, I'm looking for a number here. Yes, it will be.
So this is also 1/2, just like the 2 free ends.
Yes,
So it's a half harmonic. Is that what it's called?
that's the first harmonic.
First harmonic.
Wait, how did you get those numbers again? 60 and 2.264?
The 60 is the frequency of the vibration of this, and that frequency of this vibrating up and down is based upon the frequency of our electrical grid, which is 60 hertz.
And 2.264.
That comes from, if I'm trying to find the first harmonic, I know the first harmonic is a half of a wave, and so whatever that length is right there from string vibrator to pulley, that's a half a wave, so a wavelength is twice whatever length that is. And our tension is
18.34.
18.34.
Newtons.
All right. As this string is hanging over the pulley and I have a mass attached to it, this mass down here we will assume is in equilibrium, and therefore, as Robin said, the tension will just be the weight of the mass that's hanging. So what is the mast that should be hanging?
One point 87 kilograms.
1.87 kilograms. So I've got a 500, 1,000, a 500, I've got a 200 here. So I got 1.7, 1.8, a 50, and a 20. So that is, if I can get it to stay. All right, that's 170, or, no, sorry, 187.
Are they touching the line?
They are right now. Is this thing on? I think so. Oh, fell off that. Come on.
Dr. Fox, where do we get the 1.87 kilograms again from?
The tension right here, if you think about this point right here, I have a weight hanging down, I have tension acting up. And so, that's unplugged. If this is an equilibrium, then the tension up should equal the weight. And we assume that, it's sort of an ideal here, but we assume that the tension in the string is constant. It's the same throughout.
Okay.
First harmonic. That's not too bad. All right, I'm a little bit shy, or a little bit. So it looks like it's just slightly less than that. Take that off. Somewhat in the ballpark. Now, when trying to get the greater harmonics, it's helpful to have a much longer string. If you have a much longer string, though, you have to have much more mass hanging here. So, which is one of the issues that I had when filming it, was I think I had over 2 meters. So I had roughly twice this, and I had 4 kilograms sitting on here. So the system could not hold. And then another issue is the fact that if this is vibrating 60 times a second, that camera is filming also 60 frames a second, and so it looked like this wasn't moving. So there's a certain amount of trust in me when I said, hey, it's the first harmonic.
So I'm sorry, going back to, if this, how is it, why is it not 1.83 then?
So what's the formula for weight?
Acceleration due
And what is G?
to gravity.
Yeah, so I have 18.34 newtons is equal to the mass times 9.8. Did you use 9.8 or 9.798?
9.798 for
Okay.
bags.
All right, one other thing that we're gonna do here before we sort of shift some topics, still talking about waves. This is a frequency generator. And I want to figure out at what frequency is 500 grams going to be enough to get the first harmonic.
the tube, the water, and this?
As a lab, these were actually, this was not a lab, this was always a demonstration. The other two were two separate labs.
Oh, okay.
Okay, right now this is vibrating at 100 hertz. You can start to hear the hum there. .71 hertz, 38 hertz, and then 130 hertz, 192 hertz. All right, so let's make our predictions. We have the linear density of the string,
Are you okay?
same as always. I know the frequency times the wavelength is equal to the square root of the tension over mu. I want the hanging mass to be 500 kilograms. That's awfully large, considering my mass is about 100 kilograms. So 500 grams, 0.5 kilograms. I am going to trust the manufacturer for the demonstration purposes that they did not lie when they said this was 500 grams. So from this, how would I find the tension?
Multiply by 9.8.
Or- Let's go ahead and do 9.798 since we're dealing with specifically here. So my hanging weight is 0.5 kilograms times 9.798 meters per second squared. And someone's going to reveal the answer.
4.899. Oh, it is.
Say it again.
It is.
Yeah. That's also equal to the tension. I suspect you're primarily looking at the string there, but these masses weren't moving a whole lot, so close enough to equilibrium for what we're doing. I know the linear density, so I know the speed of the wave is going to be the square root of 4.899 newtons divided by my linear density, 0.000994 kilograms per meter.
$70.204
70.204.
meters per second.
That's got to be equal to the frequency times the wavelength. What's the wavelength going to be? Or how would you find it?
First harmonic, so it's going to be lambda equals 2L. Is that what you're asking for?
And these are pretty much going to be in the same position as they were before.
Yeah.
So we have a wavelength of 2.264 meters.
Then just divide it.
Wait a second, what was I trying to find? Oh, the frequency, yeah. So what is the frequency that will work?
Is the frequency about the same because it's coming from the wall?
No,
This device right here can change the frequency.
30.919 hertz.
Let's see how close we actually get. It's a little bit off, but not too bad. I'm assuming, again, that everyone can actually see the huge antinode there in the middle.
Yeah.
Now, it does fall apart a little bit. This is not a perfect antinode here, or sorry, a perfect node. And it could have something to do with the fact that there is a mass in the string and I've got all these little dangly things over here. But, all right, so given that frequency, or actually, no, let's do it. What frequency would get me a second harmonic? I know I could reduce the mass to get a higher harmonic. So this stays the same. That's the thing that's changing.
It's just the 1.132. Because L is equal to the wavelength in the second harmonic.
That is correct. And therefore, the frequency for the second harmonic, I'll put it to the left of 2.